Good day. This is the second video on chapter 6.3 and also the last video on chapter 6. Alright, so what are we doing today? We are going to do another extension of polar coordinates known as spherical coordinates. Now this one is a little harder than cylindrical coordinates, which you listened to in part 1. Alright, so what is the idea? The idea is to turn 3 bits of information into 2 angles and a distance. So if you have point P or vector x with coordinates x, y, z, then what you do is you project that point to the xy plane, which is vector v with coordinates x, y, 0. And then what you do is you measure the distance from the origin to vector x. So the norm of x, we're going to define that as rho. And we can connect the origin to vector x. We can call that ray 2. And we can look at the positive z-axis. We can call that ray r1. And the angle between the two rays, as indicated in green, that angle is known as phi, phi, the Greek letter phi. Also, we projected point x to the xy plane. So now we can form ray r4, which is going from the origin, passing through vector v, and the positive x-axis, we can call that ray r3. And the angle between those two rays, we use the Greek letter theta, spelled theta. All right. So we turn the 3 values x, y, z into 2 angles and a distance. All right. Now using trigonometry, you can show x is rho sine phi cos theta, y is rho sine phi sine theta, and z is rho cos phi. Make sure that your phi and theta do look different. All right. So this is the transformation. So the rectangular would be x, y, z, and the spherical would be rho theta, rho phi theta. All right. Now, a couple of remarks. Firstly, rho is greater or equal to 0 because it's a distance. We prefer phi to be between 0 and pi, and we prefer theta to be between 0 and 2 pi. So if theta is outside that interval, you just subtract or add suitable multiples of 2 pi to be in that interval. All right. Now remember what phi is. Phi is the angle with respect to the positive z-axis. So if you want points above the xy plane, then phi is between 0 and pi over 2. Remember that. If you want points below the xy plane, then phi has to be between pi over 2 and pi. Now, if you apply the theorem of Pythagoras or playing with those equations, it's easily to show that x squared plus y squared plus z squared equal to rho squared. Another fact that you should remember. Likewise, if you play with those equations, you can show that x squared plus y squared equal to rho squared sine squared phi. Please do this. All right. Now, it is important that you are able to jump between rectangular and spherical coordinates. So please do examples 185 and 186 to be comfortable with jumping from rectangular coordinates to spherical coordinates and vice versa. All right. Now, what is the Jacobian? So we have a transformation in R3. So what is the Jacobian? So if you work out the Jacobian, which is the determinant of a 3 by 3 matrix, this is a very long calculation. But when you do the determinant of that 3 by 3 matrix, it works out to be rho squared sine phi. So this you've got to remember. So the Jacobian for spherical coordinates is rho squared sine phi. And now we can state the transformation theorem for going from rectangular coordinates to spherical coordinates. So say E is a subset of R3 and it's closed and bounded, and let f be a nice function. In this sense, we want f to be a map from E to R that is continuous. Then the triple integral of f over E does exist. And now say f is all the points rho phi theta such that the x, y, z, or rho sine phi cos theta, rho sine phi sine theta, rho cos phi is the element of E. And that is a subset of the rho value has got to be greater or equal to 0. The phi values has got to be between 0 and pi, and the theta value is between 0 and 2 pi. Then the transformation theorem says that the triple integral of f over E is the triple integral of integrand over region f, being described using spherical coordinates. And you replace x with rho sine phi cos theta, y with rho sine phi sine theta, and you replace z with rho cos phi. Remember the Jacobian, very important. So the Jacobian, rho squared sine phi dv. All right, so using the transformation theorem, you can go from rectangular coordinates, a triple integral in rectangular coordinates, to a triple integral using spherical coordinates. All right, very important. Don't forget our previous tricks from before, that sometimes splitting up is good to do. And typically, if you pick your angle phi and theta, you will be able to show that rho lies between two functions u1 and u2. And this will help you to turn it into iterated integrals, as you will see in the second example in the video that we are doing today. All right? Please practice this. Do many examples. I am pretty sure you will get a question about spherical coordinates in the 218 exam. It's a very beautiful theorem, and you are most likely going to get a question on spherical coordinates, so please do practice this. All right, so let's start with an example. So let's look at this example. So E is a region above the xy plane, and inside the sphere with equation x squared plus y squared plus z squared equal to 1. We want to evaluate the following triple integral. So it's a triple integral over E of e to the power that funny exponent dv using spherical coordinates. All right, so this is the task at hand. All right, now we know that this is a sphere of radius 1 and centered at the origin, and you want all the points above the xy plane. So it is this hemisphere depicted in this picture on the left. All right, now let's make ourselves little headings and see, can we describe this using spherical coordinates. So let's look at the region. All right, so the radius of the sphere, that is equal to 1. So if you pick any point in a region E and you work out the rho value, the rho value's got to be between 0 and 1. All right, so I do not have to convince you that any point that you pick in this hemisphere, the rho value is between 0 and 1. Likewise, if you look at this, you have points above the xy plane, all right? And for any phi value above the xy plane, there is a point. So because of that, you see that phi is between 0 and pi over 2. And as you can see, you don't just have points in the first octant, but you have points everywhere. Or if you take region E and you project it onto the xy plane, you get a full circle. So that means that theta is between 0 and 2 pi. So if E gets transformed via spherical coordinates, it turns into set F, and set F will be all the rho phi theta, where the rho values are between 0 and 1, the phi values are between 0 and pi over 2, and theta between 0 and 2 pi. So you see, this region is easily described using spherical coordinates. All right, so we are pretty happy, and now we continue. All right, now let's have a look at the integrand. All right, now remember, when you're going to spherical coordinates, you only want to see rho phi theta. Can't say this enough. You only want to see rho phi theta. So the integrand is e to the power x squared plus y squared plus z squared raised to the power 3 over 2. But now, when we go to spherical coordinates, we do not want to see x, we do not want to see y, we do not want to see z, all right? But we know that x squared plus y squared plus z squared, that is equal to rho squared. Remember, that's one of the useful facts that you got to remember. And e to the power rho squared raised to the power 3 over 2 becomes e to the power rho cubed. So the integrand in terms of the variables of spherical coordinates would be e to the power rho cubed. All right, I'm just going to make another heading just to emphasize the Jacobian. So the Jacobian, if you're going to the spherical coordinates, so using rho, phi, theta, that is going to be rho squared sine phi. And now we are happy because now we can say that the triple integral becomes, so let's make another heading. The integral now becomes an integral over f of the integrand, which is e rho cubed times the Jacobian rho squared sine phi dv. And if you need to evaluate this, we need to write this as an iterated integral. So we can pick an order, and I'm just going to rearrange that, so that becomes rho squared sine phi e rho cubed. And I'm going to pick the order. This is the order you most likely pick, is d rho, d phi, d theta. We set the theta values ranges from 0 to 2 pi. Phi ranges from 0 to pi over 2 because you only have points above the xy plane, and rho is from 0 to 1. So using spherical coordinates, we've transformed the triple integral in rectangular coordinates to a triple integral using spherical coordinates with this order d rho, d phi, d theta. All right. Now this calculation is doable, so please give it a go. And if you do the calculation, you will get an answer of 2 pi times e minus 1 over 3. All right. I am not going to do example 190. So please do that by yourself. All right. I am going to do a harder example, and that is example 191. So let's first see what the problem is. Here, E is a region below the paraboloid with equation z equal to x squared plus y squared, and inside the sphere with equation x squared plus y squared plus z squared equal to 2. The task is to express the integral of x plus z over region E as an iterated integral using spherical coordinates. All right. Now it's no surprise we're going to use spherical coordinates because one of the boundaries is a sphere. All right. And if one of the boundaries is a sphere, then using spherical coordinates might make your life quite easy. All right. So if you draw it, you will get the picture on the left. All right. So you want all of the points inside the sphere, but below the paraboloid given by the equation z equal to x squared plus y squared. Now, if you look at this region, you can see if you pick an angle, phi and theta, and you draw a ray, then one of two things could happen. All right. If you pick a ray below the xy plane, you see it starts at the origin and it ends on the sphere. But if you pick a different phi and theta and you draw another ray, then you see it starts there and it ends there. Remember, you only want the points below the paraboloid. So you see that the ending values are always on the sphere, but the starting values differ. All right. So it depends on whether you are above the xy plane or below the xy plane. So let's have a look at the region. All right. So we have a rough sketch of the region, but we see that we need to split up the region. Remember I said earlier in the video, sometimes splitting is good to do, and this is what we're going to do. All right. So I'm going to say, let E2 be all the x, y, z in E where the z value is less or equal to 0. All right. So E2 will be all of the points below the xy plane. So below xy plane. Let's make it as clear as mud. We want all of the points below the xy plane. All right. Now, if you look at all of the points below the xy plane, you can see that they have rho values between 0 and the radius. All right. So if that is the equation, then the row value corresponds, so x squared plus y squared plus z squared, that is row squared is equal to 2, and row is positive, so row is equal to root 2. So you see that if you're looking at the points in region E, but below the xy plane, that row is between 0 and root 2. All right? And now you have all of the points below the xy plane, so that means phi is between pi over 2 and pi. And if you project all of the points below the xy plane onto the xy plane, you get a full circle, so theta is between 0 and 2 pi. All right, so this is taking care of the points below the xy plane. Now we got to continue, and now we got to look at the points above the xy plane. So let E1 be all of the points in region E where z is greater or equal to 0. So thus, this is the points above the xy plane. All right. Now again, it's quite clear that because you have the points above the xy plane, that we are going to have that if you project it onto the xy plane, it's a full circle. So it's easy to see that theta is between 0 and 2 pi. But you see that not all phi values are possible. All right. You see that the biggest phi value occurs when those two surfaces intersect. All right. So this will be phi minimum. So phi minimum would be when the two surfaces intersect, you're going to get one of those points. And if you take any of those points and you measure the angle with respect to the z-axis, that will be phi minimum. And the xy plane corresponds to phi is equal to pi over 2. So we got to do a little calculation. So we need to first stop and say, when do they intersect? When do x squared plus y squared plus z squared equal to 2 and z equal to x squared plus y squared intersect? Now let's think about it. X squared plus y squared is z. So x squared plus y squared, I can turn that into z plus z squared equal to 2. We want to see the details. Setup is very important. So if I rearrange this, I get z squared plus z minus 2 is equal to 0. And we are lucky, it factorizes. So z plus 2, z minus 1 is equal to 0. So we get z is minus 2. We reject, since z is positive, greater or equal to 0, so only z equal to 1. So we see that the two surfaces intersect when z equal to 1. All right? So these two surfaces, x-axis, y-axis, z-axis, they intersect in the circle, let's call it T. So T will be all of the vectors x, y, z, such that z is equal to 1 and that x squared plus y squared equal to 1. Right? Because x squared plus y squared is equal to z, so z is equal to 1. All right? Now remember, all of these points lie on x squared plus y squared plus z squared equal to 2. All right? So every point on set T satisfies x squared plus y squared plus z squared equal to 2. All right? Why is this important? Because we are interested in working out this phi minimum. What is this phi minimum? All right. Now, let's do some mathematics. All right? We need to work out what this is. All right. Now, you can use Pythagoras, you can use trigonometry, so there are several ways you can work this out. But I'm going to say, all right, I know that if I look at those points, the row values got to be root 2 because x squared plus y squared plus z squared equal to 2. So that means that for all of those points on set T, rho is equal to 2 and z equal to 1. And now remember, you always replace z with what? You replace z with rho cos phi, that's equal to 1. And so we get that cos phi is equal to 1 over rho, 1 over root 2. And so we see that phi is arc cos 1 over root 2. Since phi is in the first quadrant, it's a special angle, so we don't need a calculator. So we see that phi minimum is pi over 4. All right. So every point in set T has a phi value of pi over 4, and that is the minimum. So for region E1, we know that the phi values are between phi minimum, pi over 4, and pi over 2, which is the xy plane. All right. So now we're not done yet. You can see how interesting the setup is. All right. So we now have to do rho. We've done theta, that's between 0 and 2 pi, that's easy. We've done rho, it's from pi over 4 to pi over 2. And now we need to look at the rays. So what I'm going to do, I'm quickly going to copy this picture. So I'm going to Control C, copy this picture, and then I'm going to go Control V, pasting this picture to help me out, because now I know that if I draw a little ray, so once I've picked a theta and a phi, I draw a little ray with that theta and phi, and you can see it starts on the paraboloid when z is equal to x squared plus y squared. This is when it starts, all right? That is when it starts, and that's when it ends. So as always, we got to know that if you replace z using spherical coordinates, it becomes rho cos phi. And x squared plus y squared, I said earlier, that's rho squared sine phi. All right? Now you can see for all of those points that rho is positive, so I can divide by rho. So I get that cos phi is equal to rho squared divided by rho, which just becomes rho, and then it becomes sine, that's squared, sine squared. So then we see that rho is equal to cos phi over sine squared rho. All right? And where does it end? It ends when it hits the sphere. The equation of the sphere is x squared plus y squared plus z squared equal to 2. So if you take it slow, you say it starts with this equation in rectangular coordinates. You replace all the x, y, and z, and then you get what the rho starting value is. Where does rho end? When it satisfies x squared plus y squared plus z squared equal to 2. We know that x squared plus y squared plus z squared, that's rho squared, that's equal to 2. And we get that rho is equal to root 2. And so now we can say that rho is between cos phi over sine squared phi, and that's less or equal to root 2. So you can see, to describe region E1, which are all of those points in region E that's above the xy plane, it's a lot more complicated, all right? Theta was easy, it's between 0 and 2 pi, but we had to see that phi is between pi over 4 and pi. So that was a little calculation in itself, all right? And here again we had to do a little calculation to see where does rho start and where does rho end, all right? And so now we're not quite done yet. So we quickly have to look at the integrand. So remember, the integrand for this question was given as x plus z, but we're going to spherical coordinates, all right? So we got to say, yes, I know that x is rho sine phi cos theta, and I know that z is rho cos phi, all right? And now we can finally look at the integral. All right, so remember the integral was given as a triple integral over E of x plus z dv. And by looking at the region, we see it was important to split it up as a triple integral over E1, the integrand doesn't change, plus a triple integral over e2, the integrand doesn't change. Because if we do it like this, it allows us to describe it using spherical coordinates. All right. And now we can continue, and we can now say, all right, E1, that is the point above the xy plane. So this becomes a triple integral. Let's make it quite big, because we have bounds and lots of things to take into account. So it's a triple integral. The integrand we saw is this rho sine phi cos theta plus rho cos phi. And now because we're going to spherical coordinates, we've got to remember the Jacobian. And the Jacobian is rho squared sine phi. And then I'm going to use the order d rho d phi d theta. All right. Now looking back at region E1, we know that phi is between 0 and 2 pi. Theta is from 0 to 2 pi. Phi starts at the special angle, which is pi over 4. That's the smallest phi, till pi over 2. All right. And then we just worked out that rho starts at cos phi over sine squared phi, and it ends at root 2. So this is taking care of the points above the xy plane. And then we also have to do E2, which is all the points below the xy plane. So that's going to be another triple integral. So the integrand is x plus y, but we've got to have it in spherical coordinates. So x becomes rho sine phi cos theta plus rho cos phi. There's a price to be paid to go to spherical coordinates, so we've got to remember the Jacobian, which is rho squared sine phi, and we use the order d rho d phi d theta again. Now E2, we have theta ranges from 0 to 2 pi. It's a full circle. And then phi, these are the points below the xy plane. So this is from pi over 2 to pi. And then rho, we saw is everything from 0 to root 2. And there you go. We have transformed the triple integral in the world of rectangular coordinates to the world of spherical coordinates, but we had to split it up. And that is the reason why we have two triple integrals using the order d rho, d phi, d theta. All right. I hope you enjoyed this video. Spherical coordinates is very beautiful because as a little exercise, so try this. You can show that the volume of a sphere of radius r is 4/3 pi radius cubed. All right, so one of the cool uses of spherical coordinates is to show that the volume of a sphere is 4/3 pi radius cubed. And you can do lots of other cool things. I hope you enjoyed this video. Have a lovely day, and do practice spherical coordinates. I'm saying this one more time. Do practice spherical coordinates because it will come up in the exam. Good day.